Hi, everyone. My name is Moham Arif. I'm with Relational AI. With me is my colleague, Jay Yu. We're here today to tell you about building mission-critical intelligent applications with relational knowledge graphs on Snowflake. So very quickly, let me define what I mean by mission-critical applications. So I'm referring to a term that comes from a Geoffrey Moore framework on core context. This Geoffrey Moore analyzed enterprises, describes how in most enterprises you have two types of processes: mission-critical processes. These are the processes that touch most of the revenues of the business, and then non-mission critical processes. These are experimental, departmental, maybe local processes where maybe innovation happens. And if a process sort of starts to have a positive impact on the business, it can be deployed more broadly in the business. Typically, you have applications supporting these processes in the non-mission critical part of the business. These are applications that might be written in Excel or in simple no-code tools or in two-tier architectures, et cetera, because they're not going to be used by lots of people. Whereas the mission-critical applications that need to be written in a more professional, industrial strength way because they drive a lot of the revenues of the business. Geoffrey Moore also talks about these processes being either core or context, meaning core is differentiating processes and context meaning commodity processes, but that's less relevant for what we're talking about here today, other than to note that intelligent applications have the potential to be differentiating and driving a lot of the value in the business. Okay, so what are intelligent applications? Intelligent applications leverage AI to improve decision-making. They're often used to make high-level business decisions, for example, deciding on how much capital to allocate to fundamental drivers in the business. In retail, you want to decide how much capital to allocate to inventory or to labor or to real estate or to customer acquisition. In manufacturing, you might want to make decisions about how much raw material to buy, how much manufacturing capacity to invest in. In telco, you decide on how many cell towers you want to have, how much equipment to put on each tower, how much wireless spectrum to allocate to different parts of the country. So intelligent applications in general help business people understand what happened, which is sometimes called descriptive analytics, what's going to happen, which is sometimes called predictive analytics, and then what to do about it, which is sometimes called predictive analytics. Descriptive analytics can come in different flavors. You can have the BI flavor or the graph analytics flavor for understanding communities and pathfinding and so on. Predictive analytics are used to drive things like or understand things like future demand, predicting risk, predicting fraud. A lot of machine learning is used here, but sometimes simulation technology is used as well. And then prescriptive analytics are used to help you decide, what kind of products to carry or what the price of each product might be or when to order new products. Here, a lot of solver and optimization technology can be used, sometimes reinforcement learning. And the solver technology can be integer programming, linear programming, quadratic programming. Okay, this is non-trivial stuff, but the world runs on these types of technologies because of the impact they have on the efficiency and robustness of supply chain networks, for example. Okay, intelligent applications typically have fewer users who look at more data than transactional applications. So on the order of hundreds of users in an enterprise that are making decisions about how to allocate capital versus, say, millions of users or customers of that enterprise that are buying products online. These enterprise users are typically looking at lots of data because they're trying to analyze patterns from sales history, for example, of tens of thousands of products being sold in over 1,000 stores or across thousands of days as well. These types of applications have historically been built on three-tier architectures that combine different technology stacks, each with its own data management and programming model. I already referenced some of this earlier, but historically, when I had to build applications like that, we've had an operational stack, an analytical BI stack, an analytical graph stack, a planning stack, a predictive stack, a prescriptive stack, again, each with its own data management and programming model. Very often we're expressing semantics procedurally. And of course, all of this leads to soul-crushing complexity that creates convoluted applications that are no fun to build and certainly no fun to use for their end users. So very quickly, of course, we all know what a traditional application architecture looks like. It's typically a three-tier code-centric architecture with the data for our purposes today in Snowflake, but the semantics and the business logic expressed procedurally. In this incarnation of this architecture, we're talking about expressing it in JavaScript, running it in Express on Node.js. And then, of course, the presentation layer, the user interface, is often developed in JavaScript using frameworks like React. But of course, there are many manifestations of this depending on the programming language of choice. There's a Java version or multiple Java versions of this, multiple Python versions of this, C# versions, and so on. But the core architecture here is three-tiered. You have the data in SQL and Snowflake. You have the programming language defining the business logic and a different programming language describing the user interface. The architecture we're talking about today is more data-centric. It's still a three-tier architecture where the data is in Snowflake, but the logic is also in Snowflake, implemented using relational AI's relational knowledge graph. And so this relational knowledge graph is a native app running on Snowpark container services inside Snowflake, and it creates and organizes data as a set of relational views or dynamic tables on the underlying data in Snowflake. And so it organizes it in something we call graph normal form. It's a highly normalized way of looking at data. And this gives us a lot of versatility in terms of being able to manage dynamism in an application. You can add and remove new data without having to restructure denormalized data and do schema surgery. The logic itself is also expressed relationally and effectively defines new views, new relations, new dynamic tables in this relational knowledge graph. And this logic is, because it's implemented relationally, you don't have to worry about parallelizing it or scaling it beyond what fits in memory or incrementalizing it or any of that stuff. It's all comes for free just by expressing the business semantics. And then, of course, to make it possible to support intelligent applications, this relational knowledge graph supports graph analytics, predictive analytics, prescriptive analytics, what is often called composite or compound AI these days. And of course, the presentation layer can still be developed using JavaScript and the traditional technologies for developing a user interface. So with that, I'm going to hand over to my colleague, Jay, who's going to walk us through a concrete example and show us a lot of code about how you can do this. Jay, over to you.
All right. Thank you, Mohan, for the great introduction. Let's first talk about the example use case we're targeting for building an intelligent application using relational knowledge graph. We're going to actually talk about a supply chain. If you want to buy a bottle of water, this is the underlying supply chain supplies it. You have to first source the raw material in terms of spring water and plastic bottles. You have to actually making sure you have bottling company to bottle the water, to pack it, to send to warehouses, and finally before reaching to the retail store. So it's actually kind of complicated because you have to figure out how to source, how to make. Make involves resource capacities, machines and labor, how to pack, and then how to find the best way logistic to ship with reasonable cost to warehouse, figure out the inventory management, and then finally deliver to the customer based on demand. So there's a lot of time-sensitive information need to be weaved on top of it in terms of capacity, inventory, customer demand. How do you plan all the parts of the supply chain to fulfill demands and maximize for profit, optimal for a lot of various business metrics? Now, in order to build such an intelligent data application, we start with data. Data is the foundation in Snowflake with massive data cloud. You organize the data into those relational SQL table definitions with all the various tables and then with relationships. When you put all these data into Snowflake, it's really optimized for persistence, performance, scalability, and then also massive relational analytics you can perform on the data. Now, with relational knowledge graph, we help you to actually elevate your implicit, foreign key relationship SQL join into explicit relationship by modeling the business in the most natural way. In this case, I turn each table, into a business entity with meaningful names. I also make those implicit relationship, foreign key relationship and joins into a name relationship called in the SKU at side is actually at side is reference a specific business object on the side. Also, we can allow you to actually refactor or decompose a white table into making sure the business entity involved explicitly extracted out and externalize the relationship. So with that, we're able to enhance the data in Snowflake with a relational knowledge graph views on top, but with enriched data and semantics to form a knowledge graph, and sometimes it's called ontology. So let's actually jump into the code to see how we can allow you to do all of that with our Python language support. What I'm showing you here is actually a Jupyter notebook, even though everything is expressed in Python, but these Python-based rules are really executed natively inside Snowflake, closer to the data view, Snowflake container service, as well as native app. We're declaring a type called site. It mapped to a site table, and then we want to declare a local variable in Python called site. And we do the same thing for SKU, as well as SKU and site combination. We are adding derive a new relation or new property associated with SKU and site called for SKU. Underneath it, we do all the magic, directly connect the SKU at site object with the SKU object. So you no longer need to rely on joins to stitch things together. We're doing the same for at site. So we give you the ability using rules to declare a query. And this particular query literally say for all entities in SKU at site, and find the ones matching SKU 002, its SKU ID 002, and then using those explicit meaningful relationship, pull out its name, pull out the site name and SKU name. As a result, if you execute on that, we can quickly return what's for SKU 002. I did mention, bill of materials, and this is just a few lines. The base component is called BOM component, match one-to-one to a bill of material each rows. Each rows has both input and output. Output got repeated for each input. This is where we're able to abstract a new entity called BOM master. And then the BOM master and the BOM component can be connected directly with a meaningful relationship called has component. So BOM master.has component will help you reach out to BOM component all the details. We can help you easily project from this knowledge graph to a simpler construct called property graph. Property graph sees the whole world as nodes and edges. And then that's exactly what we're doing. We map with this few lines of code, we map BOM master as a node in the property graph, components as a node. And then how do we get components? We navigating the has components relation. And then also we make a connection between the BOM component and BOM master, make that as an edge. After we're doing that, with all the display attributes specified, we're able to visualize what the bill of material look like. One of the areas I want to highlight is if you also help you define business rules, derive new meaningful properties. In this case, this few lines of code, what we're saying is we want to calculate the total lead time at operation level. And it's defined as if there's no operation steps, I want to set this to be 0. Otherwise, I'm going to sum all the durations from each step. So now, once we add all the operational details, combined with the bill of material, combined with the the side SKUs, we can again, creating a more comprehensive property graph. And one of the first things we can do is to help you visualize this property graph. You can probably remember from the slide I shared earlier, this is actually, we created a digital twin of the configuration of the supply chain. So again, with only just a few lines of code, we model the business domain with relational knowledge graph, create a view on top, and then give you the ability to have a visibility into how these supply chain is connected to each other. The other benefit is when you construct this property graph, we have a huge library of graph algorithms, graph analytics tools to help you to analyze the graph, to find insight. Just 3 lines of code, 2-3 lines of code, we're able to help you to find that. So let's look at the code. the first thing we need to do is find all the SKU at site with SKU ID is SKU 002. We define that as starting nodes, could be more than one, right? And then we literally pass that to a graph algorithm function called reach from. It's a reachability. We internally do a recursive processing using our rules and quickly, efficiently find out all the downstream dependencies. And then once you find those reachables, we allow you to actually basically navigate its properties. And now you find out, say, these are all the places plastic bottle have an impact on my supply chain. We derive a new concept called time period. Usually in the relational Snowflake tables, usually it's modeled as two columns, begin period, end period. We just create a new business entity and type called time period, and we can consolidate all this information into a meaningful construct, and that could be connected to any entities. So with all these information plus customer demand included, now this graph gives you the full picture. It's a digital twin of the whole thing, more than just the network graph design for the supply chain, but also now we lay out incrementally the new information about at what time, what availability of inventory, resource capacity. Now the next part is really about doing the optimization. Let me show you a little bit of code behind this. This particular function called optimization mode allow you, again, define new types if you want. But one of the key things that you have to tell us, what are the variables that matters? What are the variables? What is your objective? Very declaratively, in this case, we try to minimize unmet plans, right? We want to make sure we can fulfill all the customer order. We define the constraints. There's some of those are a little bit more complicated, time-based. Some of those are more simpler in terms of bounding. What's the upper bound, lower bound? These are the constraints. Capacity, there's only this much. And then finally, once you declare all these, and you can just simply call one function, solver.minimize, and we will give you the best solution for this problem. Okay, coming back here, you can choose to persist the solution into Snowflake. The next step in our code is we allow you to, again, enrich our knowledge graph with all the planning output, which is the PEG, and then we define, understand the result of the planning, oftentimes more than just operation I shared, but also you can draw from inventory. You can actually reuse a leverage capacity. With that also combined, we are able to also construct the PEG table. The result usually is recursive. There's a mutual dependency. I'm going to do this, but I'm going to rely on my parent, which is my upstream, deliver this to me. So simple, just one or two lines, we allow you to construct that rich relationship. Once you have all these combined, we project to the graph. Guess what? Now we show you the final result. Well, there's actually two customer demand coming in. One seems like I don't need to even invoke any my manufacturing. There's enough inventory at my warehouse, enough inventory in my upstream factory. I can just combine them to deliver. And then the next order, we need to invoke the entire supply chain, right? We need to start with raw material, drawing 1,000 bottles, 1,700 ounces of water, and then with resources, we'll produce that. So with that, that concludes my basically code demo.
Thank you, Jay. That was great. Thanks for the demo. So let's wrap up here. We have a few minutes left. What you saw Jay do here is using Python, using standard tools, the tools he enjoys using. He was able to configure and set up a knowledge graph without having to learn any kind of technology he didn't want to have to learn, defining the core concepts of the business and defining relationships between them, and then defining relational rules described in Python for modeling a really non-trivial business. For those of you who've done this before, working with bill of materials and working with the matching supply and demand and all of that, it usually takes a lot more code. So the whole setup that Jay showed you was about 626 lines of reasonably well commented code. And he found time to throw in a little visualization here and there just to entertain himself. And then of course, the business logic that he implemented, again, describing it in Python, but really what he's doing is building, using Python as a rule builder, as a query builder to just define sort of relationships in this knowledge graph that you can use as building blocks to define more and more sophisticated relationships and more sophisticated views that describe the business logic. Okay, and so he did a bunch of non-trivial things in that, including using recursive logic to describe bill of materials. The other thing Jay showed you is how to work with prescriptive analytics. Again, underneath the covers here is a very sophisticated integer programming solver that is just there. It's as if it was built into the programming model, and using the same types of rules he used before, he used those rules to define an objective function that he wanted the solver to minimize or maximize. An objective could be like, I want to make the most amount of money, or I want the least amount of risk, or I want for my supply chain to be robust, or I want it to be environmentally friendly. All of those things can be part of an objective. And then he described the constraints that must be satisfied by the solver, also using similar relational description of constraints. Don't work more than 40 hours a week, or avoid using routes through this mountain range in the winter, things like that. These are all can be expressed relationally as well. He also showed good examples of leveraging graph analytics. Of course, supply chain networks are networks, and networks are graphs. They're sort of directed graphs. And there was no reason for him to go develop a bunch of code in a one-off way. So you can see here on the right, there's a lot of built-in graph analytics. And then, of course, if it's something that you want that isn't built in, you can just write the rules to express the graph analytics using self-joins and recursion and things that would be hard to do in a traditional SQL implementation, and certainly very hard to do procedurally in Java. And finally, what he didn't show, we'd love to show you at a future event, is how this model, or this digital twin of the business, with concepts around product and distribution center and supply and demand and all of that, can be verbalized in natural language, so that you can share that description with a language model that's trained on the world, but not trained on your business. Okay, and so even if you wanted to train it on your business, you need to give it a description of your business. So whether you're fine-tuning a model with a description of your business, or whether you are providing a description of your business via prompts, you can take this model in a high-level way and express it in natural language, and then feed that into language models so that you can create agents and do other really interesting things with Gen AI. More coming here. I would love to show you more in the future. Very quickly, I want to just talk about a couple of case studies. So this supply chain example that we used here was inspired by our work with a company called Blue Yonder. They're the leader in the supply chain solution space. They have very complete, very sophisticated solution for supply chain planning and supply chain execution, with lots and lots of different modules. Some of these modules have been written a long, long time ago and need to be modernized. And so they gave us one such module that was written in the 90s in C++. And this module is called Supply Chain Strategist. And in about 4 months, 4.5 months, we were able to, in effect, throw away a lot of the C++ code, because it doesn't do anything. A lot of it isn't about expressing the business logic. And the parts that were left over, about 205,000 lines, we implemented as a knowledge graph, leveraging the prescriptive and the predictive and graph analytics capability that's built into the knowledge graph. And in about, let's say, 10,000 lines of rules in SQL, it's a little bit less than that, actually, we were able to implement the same business logic, the same semantics, with the same analytical sophistication, running faster, running with larger data sets, et cetera, because we were leveraging the relational knowledge graph. So that was a really compelling example of the use of this technology. In fact, once you actually just look at the essential semantics of this application, you can verbalize it and describe it in about 20 pages. So think about 205,000 lines of C++, and all the accidental complexity that is embedded in that relative to 20 pages of business logic. We saw something also very similar working in the tax application space, where we used rule-based reasoning and graph analytics and other types of sophisticated analytics. And in the end, 800,000 lines of C# or so was replaced with about 15,000 lines of SQL and rules. And in one really extreme example, about 100,000 lines of C# that were doing some very convoluted, very sophisticated tax logic were replaced in these 7 pages here of logic. Really amazing code compression. Again, because you're not having to worry about a lot of the accidental complexity and parallelization, incrementalization, and memory management, and algorithm selection and data structure selection. All of that goes away because you're just expressing the semantics. You can find out more about the Blue Yonder case study by going to seeing the recordings from Summit 24. The talk was called Supply Chain Strategist. We also have talks from our work with Cash App, where really interesting work on applying knowledge graphs to their problems. And then at Summit 23, AT&T gave a talk about how they use our relational knowledge graphs in their context. Okay, so in summary, I'm just hopefully you can see how data-centric architectures based on relational knowledge graphs are effective for intelligent applications. We're not alone doing this. I think some of some most interesting companies with the most sophisticated technologies, like the Amazon retail business, is built on a little-known technology called Sable and DataPath. They don't really like to talk about it, but you can find out about it by going and looking at the job boards, and you can learn more about Sable and DataPath as basically a super scalable database and a rules language that implements the entirety of Amazon retail business logic and so on. Google Ads is run similarly on a system called Napa. Jay actually worked at Intuit, and he helped build a knowledge graph management system that's used to implement TurboTax, a very non-trivial piece of software that has to ship regularly every year. Salesforce is built on poor person's knowledge graph. It's basically a 4-column table in Oracle that has tenant, entity, attribute, value. And then if you are aware of Palantir, you know that they go out of their way to explain how they use ontology and knowledge graph to build their applications. Okay, and at their core, relational knowledge graphs eliminate much of the accidental complexity that you have to express in an application by minimizing state management. You don't have lots of services implemented across lots of stacks. Simplifying control flow. Instead of having lots of event handlers, you basically, a lot of it becomes data flow. And then, of course, minimizing the amount of code. And then I'll close by making an announcement that we're happy to announce general availability of the relational AI knowledge graph as a native application using Snowflake Snowpark container services. And what will be going GA today is the rule-based reasoning and the graph analytics with path queries. We are still in private preview for both the prescriptive analytics with linear programming and mixed integer programming and quadratic programming, and for predictive analytics with graph neural networks. There's a lot of cool work that we'd love for you to check out and let us know how to make it better. Lots of improvements and new capabilities are on the way. And with that, we'll close out. Thank you for your time. And please reach out to us via our website over the Snowflake Marketplace or the Snowflake Solution Center.